Now let's look specifically at proportions for our confidence intervals. We have our generic formula that we had earlier, but now we're going to apply it to proportions. So we have a parameter, but this time instead of using mu, we're going to use rho or p. Our statistic is going to be our p hat, which is our sample proportion. We have this approximation to the binomial distribution, something that we get when you have enough coin flips. Essentially, you end up getting that normal curve out of those repeated coin flips. That's kind of what we're getting here with our way of figuring out how far apart, what is the standard deviation or the standard error in that curve. So we'll look at that formula a little bit more in a bit. And then the last part is z star again, which is the z-score given our confidence interval. And together those form the margin of error. We again have conditions. Just like before, the first two are the same. So data has to be from a random sample, like a simple random sample, and the population size has to be greater than or equal to 10 times the sample size. So you need a much larger population than your sample. An example of breaking that would be if we were to take a sample of 100 students in a school of 600. We would be violating that condition, so our confidence intervals might start to run into issues. The last one here is we need to have at least 10 successes and 10 failures. And what that means is there needs to be, essentially, if you're asking a yes-no question, at least 10 people have to say yes and at least 10 people have to say no. Success is the thing that you are looking for. So if you are saying, what is your favorite color, blue or not? If blue is considered a success, then you would need at least 10 people that say that and at least 10 people that rejected that. Now let's look at an example. It says, at the same factory, you take an SRS of employees to get their opinion on their product. You want to know whether or not they would recommend what they make to friends for purchase. 41 out of 55 said that they would. Find a 99% confidence interval for the population proportion. Now let's check our conditions first. We have data from a random sample. It looks like here we have an SRS. So yes, an SRS of employees is going to be a random sample. Next one, population size is greater than or equal to 10 times the sample size. Well, if we're taking a survey of employees and we have 55 in our survey, I would actually be a little bit worried about that. It doesn't tell us how big this company is, but a factory having over 500 people, that would be a very large factory. So that's something I'm a little bit nervous about. So we don't have any evidence to specifically refute that, so we are going to continue to do the problem, but just be aware that that condition might be a little iffy. Last one is at least 10 successes and at least 10 failures. Here it says we have 41 out of 55. So that means we have 41 successes, and if you subtract these, there are 14 failures. So yes, it is at least 10 on each side. And if you want to just get a quick example of why that condition might matter, let's take a look at StatKey. What I have here is the curve generated when you type in the 41 out of 55 if you're doing your confidence interval using bootstrapping here in StatKey. Now, if we were to edit our data and change this to something, let's say 48 out of 55, so we're within that 10, we don't have 10 failures. If you generate your resamples, you can see that your curve is a little bit less of a normal curve. We start to see a little bit of skew appear. You kind of see this long trailing off towards the edge. Even when you have lots of resamples to smooth it out, it's not quite normal. And when you get really close to the edge, let's say we do 52 out of 55, where we have only 3 failures, you can see where it really starts to bunch up, and the normal curve is no longer a good approximation for this distribution. So that's why, since we're using the normal curve as an approximation, you have to make sure that it's actually going to approximate it well. We need at least 10 successes or failures. So let's get back to solving this problem. I see here that we need p hat at least 3 times in solving the problem. So let's go ahead and figure out what p hat is. Now it is the proportion that comes from our sample. So right here we have 41 out of 55. 41 divided by 55. That's going to be our p hat. And we could leave it as a fraction, but it's probably going to be easier to work with if we just turn it into a decimal. So 41 divided by 55, and you get 0.745. So now when you're writing out your formula, you're going to again try to solve for the population proportion. So that is what we were asked to find, the population proportion. And to do that, we're going to start with our sample proportion, our p hat, which we calculated right over here, 0.745 or 74.5% of that sample. So we'll write that down, 0.745. And then we're going to do our plus minus, and we have to calculate our margin of error. And this is that calculation that's a little bit on the ugly side. So we'll write our big square root. All this is doing here, if you were to simplify this down, is say take the probability of success, 0.745, times the probability of failure. 1 minus this is going to be 0.255. If 0.745 is the probability of success, 0.255 is the probability of failure. So 1 minus p hat is just your failure. So success times failure, and then you're going to divide that by your sample size and take the square root of all of that. So we have 0.745 times 0.255 divided by our sample size of 55, so this is going back to the actual numbers, and that is going to be our margin of error, or our standard error, times our confidence level. So in this case, our confidence is 99%, so we need to go back to our table, and 99% confident, in this case, 2.576. So we multiply the whole thing by 2.576. So now let's plug that all into our calculator. The first part's alright, the second part, the margin of error needs to all be boiled down. So if we have 0.745 times 0.255 divided by 55, get that inner part, and then I'm going to take the square root of that, square root, and I do second minus sign, or second answer. So now I have this first part here, this is the standard error, is 0.0587, and then I'm going to multiply that by the 2.576, and now I have my margin of error, 0.15. This is about a 15% margin of error in either direction, and when we have a sample size of only 55, that's pretty typical to see that. So we're going to say 0.151. 745 plus or minus 0.151. And that is our confidence interval for the proportion.